We'll now do a little summary of the three common physical states of matter before we focus on solids a little bit more. So we know that solids have a definite shape. Liquids and gases have indefinite shapes. That means liquid and gases are fluid. Their shape changes as they flow into different containers. But solids have definite shapes. So the these are switched. That's funny. The definite shape of this solid comes from the rigid location of the molecules. So the molecules are in a set location, and they do not have much motion. They still have vibration motion, but they do not change location much at all. Whereas for liquids and gases, the atoms and molecules are in active motion. They keep changing location, which is what allows them to flow and be fluid. Solids and liquids both have a fixed volume to them, and gases have a variable volume. Another way of saying this is that the compressibility of solids and liquids is negligible. We cannot change the volume by compressing it to any significant degree, but we can change the volume of gas by compressing it, so it has significant compressibility. The reason for these properties is that in the solids and liquids, the molecules are close packed. They are against each other. They are pushing up against each other. Whereas in gases, they are widely spaced. There's space in between them, lots of space at times in between them, so that they can be compressed. And then there's a small thermal expansion for solids and liquids. It tends to be smaller for solids than for liquids, but it can vary a little bit. Small thermal expansion, so when we change the temperature, the volume does not change much. Whereas we have a noticeable thermal expansion for gases. The intermolecular forces are strongest for the solids. They are holding the molecules in a fixed location. And then they're weaker for liquids, allowing the molecules to slide over each other. Then for gases, because the molecules are so far apart, the intermolecular forces are negligible. When they become noticeable in gases, we no longer have ideal gas. So we start to see the intermolecular forces when gases deviate from ideality. Some repetition on this one. With only one new line here, entropy. Entropy. Entropy is often called disorder. That's because when we have a high entropy state, it's hard for us to predict the exact state that we're going to have. But entropy really is a measure of possible states. So when we have a high entropy state, we have a high number of possible states that we can have, which means that it's hard to predict which of those states that we'll have. So entropy is the number of possible states. So in solids, especially for crystalline solids, the entropy is really low. So for perfect crystal, all the atoms have their set location and the entropy is extremely low. As we leave the perfect crystal, we get a lot of defects. We get crystal edges. The entropy increases as we have more ways that we can rearrange these atoms. For liquids, the molecules are moving all over the place, so we have a lot more arrangements of the atoms and molecules. So the entropy is noticeably higher for the liquid than it is for the solid. And for the gas, with the molecules, with so much space in between them, there's a extremely high number of positions for the molecules. So we have a high entropy for this. So we've already gone over the covalent intermolecular forces. Covalent intermolecular forces were the hydrogen bonding, the dipole-dipole, and the dispersion intermolecular force. Metals have their own type of bonding where electrons are shared in a valence level. Ionic solids is a pure electrostatic attraction between the positive and negative ions in the solid. And then for mixtures, we can get ion dipole. So when we dissolve an ionic solid into a polar liquid, we can get a ion dipole attraction. The strongest solid that we can get is the covalent network solids. Covalent network solids, we should have examples coming up. Covalent network solids is covalent bonds connecting all the atoms together. A couple examples here would be diamond, which is a three-dimensional network of carbon atoms bonded by covalent bonds, or graphite, a two-dimensional network of carbon atoms bonded by covalent bonds, but where the sheets are only attached together by dispersion forces, so the sheets tend to slide on top of each other. So I can go to a different spot here. So covalent network is tends to be our strongest material. That's why diamonds are extremely strong. We can use diamonds to as an abrasive material on drill bits. We can cut glass with diamonds. So this is a network of covalent bonds between the atoms. For metallic bonding, we have the metal atoms and a lattice work that's holding them together, but we're forming a valence band of electrons where the valence electrons can travel throughout the metal network. This is what gives the metal the electrical conductivity that is distinguishing of metals. This makes the metals a strong bond, not as strong as covalent, and not necessarily as strong as ionic. For ionic attraction, we have positive and negative ions alternating throughout the solid. And it's this pure electrostatic attraction that is holding these charges together, the attractive force between positive and negative that is holding these attractive forces together. These tend to be, all have high melting points. We have very few ionic materials that are liquid at room temperature. We discovered a class of them this past decade, but generally most of our ionic solids are solids at room temperature, so they have a very high melting point. They have poor thermal and electrical conductivity. That's why we use ionic solids, ionic ceramics, as electrical and thermal insulators. So when we look at solids can be either amorphous or crystalline. Amorphous solids lack long-range molecular order. So there's no general structure of the molecules in the amorphous solids. Glass would be one example. Plastic would be another example of amorphous solids. Amorphous solids might be of a material that is difficult to form crystalline solids, or just was frozen fast enough that it was not able to rearrange the molecules into proper crystalline form. Crystalline solids have a long-range structure to it, so it has a well-ordered structure. We usually end up with little crystals that we get that exhibit flat surfaces and then definite angles between the surfaces or faces. And we will look at a couple simple types of crystalline solids in the next video.